Can a 180-pound man possibly raise a 500-pound rock? Yes, if we give the lever a 10 times mechanical advantage, which we can do by making the lever longer on one side, or in technical language, by moving the fulcrum. But notice that you give up the amount of travel or distance you get at the output end. Nothing wrong with that, mind you, if you don't have to move something very fast or very far. It's great for moving boulders. What has all this to do with hydraulics? Plenty. The principles of hydraulics show properties very similar to those of the lever. Liquids can provide exactly the same physical power as the lever and offer some unique advantages in addition. If you press down on a confined liquid, the force, all of it, is transmitted evenly to all parts of the container. That's because liquids are not compressible. In fact, in a closed, sealed system, liquids will transmit just as much force as a solid steel rod. For example, you can transfer through hydraulic lines just as much force as you can with a solid mechanical linkage. And if the system is full and tightly sealed, the force is instantaneous. And what's more amazing, just as a mechanical lever allows us to multiply our power by using mechanical advantage, a hydraulic lever can be made that will do exactly the same thing. Pascal's law states that in any closed hydraulic system, pressure exerted anywhere is transmitted undiminished to every part of the system. Let's take a closed system with two unequal-sized cylinders connected by a pipe. The small cylinder has a diameter of about 1 inch. The larger is 6 inches in diameter. Now let's apply a force of 1 pound to the piston in the small cylinder. The 1 pound force is transmitted instantly to all interior parts of the system with a pressure of 1 pound per square inch. But notice that the force is multiplied 36 times on the 6-inch diameter piston, since the reaction area is 36 times greater. And just as we did with the mechanical lever, we lose something when we apply mechanical advantage with the hydraulic lever. A 2-inch piston travel in the small cylinder causes only 1/18th of an inch of piston travel in the large output cylinder. Exactly the same lever principle is used in hydraulic brakes. When a force of 50 pounds is applied by foot to a 1-inch diameter master cylinder, a 3-inch piston at the wheel will multiply the force to 450 pounds at the brake friction pads. Now, we should take time to look closely at the differences between fluids at rest and fluids in motion. We'll find that there are certain laws which apply to one that do not apply to the other. For example, the pressures in a standing liquid are the same at all points at the same level. But we'll see that this law does not apply to liquids in motion. Pressures in a moving liquid are much different than pressures in fluids at rest. Let's say we have a liquid being pumped into a tube, and there is a restriction in the tube, a small hole properly called an orifice. Until the area in front of the orifice fills up, the pressure will be 0. Then it will climb to a value dependent on the pump pressure and the rate at which the liquid flows through the orifice. As the system fills and keeps flowing, the pressures might look something like this: 10 pounds per square inch in front of the orifice, 8 psi at the orifice, and theoretically anything from 10 psi to 0 after the orifice. The Venturi effect at the restriction will cause the speed of the flow to increase and the pressure to decrease at the orifice. The important thing to remember here is that there's a pressure drop at a restriction or orifice in a flowing system. Another important point to remember is that if the system is now closed at the output end, Pascal's law takes over, and the pressure at all points is equal to the pressure per square inch at the greatest point, in this case, the pump outlet. Hydraulic valves are inserted into a system to perform a variety of operations. A simple but highly effective flow control device is the check valve. One form uses a freely moving ball, which moves with the stream and allows flow one way but not the other. This is called a ball check valve. A restraining spring may be added to regulate the pressure at which the ball opens the line. If the spring tension is made adjustable by threading the spring retainer, the valve becomes an adjustable relief valve. A poppet valve works in exactly the same way as the ball check, but uses a disc to block the flow in the reverse direction. A needle valve is usually a screw-controlled valve that can be adjusted manually for extremely low flow rates, or even to zero flow. Spool valves are precisely machined, spool-shaped valves that can serve a number of uses in a hydraulic system. The spool valve's widest diameters are called lands, and the narrow spaces between the lands are known as annular grooves. A spool valve operates in a precisely machined hydraulic passage. The tolerances between the lands and the passage are so close that the hydraulic flow can be diverted or restricted completely by the position of the land. The spool valve may be operated manually, for example, against a spring. Here, ports 1 and 2 are blocked by the lands, as ports 3 and 4 are open to oil pressure. Moving the spool valve against the spring opens ports 1 and 2, allowing simultaneous oil flow across the valve through both ports. In addition to manually or mechanically operated spool valves, hydraulically actuated spool valves are frequently used. These are usually valves with different diameter lands. Because of their action, they are called differential valves, and they can be used to regulate oil flow and oil pressure. Again, we have outlet ports blocked by the valve lands at 1 and 2, and ports 3 and 4 are open to oil pressure. But in this case, land number 1 has a greater diameter and therefore will have a greater reaction to pressure, according to Pascal's law. Then, if the force generated by oil pressure is stronger than the spring force, the valve will compress the spring and open ports 1 and 2, allowing oil to flow. And if there is no restriction beyond the port, the pressure will drop until the force is balanced against the spring load. In this mode, the spool valve would be acting as a pressure regulator and is called a balanced valve. The automatic transmission valve body uses a number of spool valves for both manual and balanced operations. The manual valve, connected to the shift lever, directs oil flow to the appropriate circuits: park, reverse, neutral, drive, second, and low. Balanced valves, meanwhile, are regulating pressures in the system. The torque converter control valve maintains torque converter operating pressure. The main pressure regulating valve maintains the line pressure at specified limits. The throttle valve regulates pressure according to throttle position. The shuttle valve regulates flow to control kickdown shift quality. Spring-loaded servo pistons, in turn, respond to the oil pressure directed by the control valves and operate other parts of the system, all executed powerfully and precisely according to the simple laws of hydraulics. Some hydraulic systems require a steady flow of fluid, and therefore a pump is necessary to provide a continuous supply. A power steering pump is a good example of a positive displacement rotary pump. That is, one that puts out a definite quantity of liquid for each revolution of the pumping member. A pulley-driven shaft drives a rotor with movable vanes. The vanes are pushed outward by centrifugal and hydraulic force and follow along the inside of a cam, which is wide at first, then narrows to a very small area. Oil is forced up through a pressure plate from both sides of the cam at the narrow points, and a positive delivery is maintained in the high pressure area above the plate and at the flow control valve. An automatic transmission pump uses an eccentric cam action to achieve the same effect. As we've seen, hydraulic systems operate with great ease and precision when the system is completely closed and free of air. Since air is extremely compressible, its presence in a hydraulic system cannot be permitted. Therefore, bleeding hydraulic systems of air is an absolute requirement. Needless to say, a hydraulic system is no better than its seals. Seals, as well as other rubber parts, such as connecting hoses, can swell or shrink, harden or soften, depending on their age, on the composition of the hydraulic fluid, and on the operating temperature. For that reason, only the hydraulic fluid specified for a particular system should be used in that system. Hydraulic seals may be classed as positive or not positive. A positive seal will effectively stop all fluid flow past the seal. An O-ring is a positive seal that works equally well in both directions. Where motion is greater and repeated many times, the seals may be steel rings, as in the automatic transmission's highly active kick-down servo. Lip-type seals are also positive seals that can be used to seal high pressures. The seal is installed with the lip facing the fluid pressure source. The lip balloons out under pressure, which aids in the sealing action. Hydraulic systems and circuits provide some of the most precise and practical devices used in industry. Also, unlike mechanical systems, hydraulic systems are usually self-lubricating. Add to that the fact that modern synthetic sealing materials have extremely high heat and chemical resistance, and you see why the hydraulic systems are among the most trouble-free and long-lasting in industry.